Hello, and welcome to the ENME 351 video lecture series. This is part one of a three-part installment in which we will be exploring digital signals and logic. The core concepts we'll explore in this lesson include analog versus digital signals, as well as an exploration of base systems, such as base 2, base 10, and so forth. So what do we mean by a digital signal? Well, to understand what a digital signal is, we first have to digest what we mean by an analog signal. So analog signals are continuous in space and time. So let's take a look at the lower left figure here. If I have a function, say of a voltage or a temperature that is a function of time, then an analog signal can occupy any value, any voltage or temperature, let's say, with respect to time. Digital signals, on the other hand, are really limited to a certain number of values. So let's say I have that same system, same sensor, let's say, with respect to a voltage or a temperature in terms of time. If I look at that signal that's continuous in an analog sense, if I look at that signal now in a digital sense, well, it's going to be limited to a certain number of values. And the most common configuration here is a binary system. So binary meaning 2, right? So that same sensor, that same system on my figure at left may have a similar output in terms of voltage or temperature with respect to time as I see here, where my voltage or temperature, let's say, is only occupying two values. Let's say a higher value and a lower value here, right? And that's driven by this binary nature of the digital signal. So what are the advantages of a digital signal as compared to an analog signal? Well, the primary advantage, as it turns out, is considering noise effects of my signal and of my system performance. So if you look at the lower figure here, if I have an analog signal, again, that's continuous with respect to time, if I have a noise component on that analog signal, it becomes increasingly difficult to evaluate and to confidently say, well, what is the true signal in the presence of that noise? However, if I look at my digital signal at right, if I have a noise component on top of my digital signal now, well, it's still relatively easy for me to set a threshold and confidently say which value, which state of my digital signal is above and below that threshold. So what is a high state and what is a low state, let's say? Okay? So even in the presence of noise, this digital signal is quite robust, and we find this being very advantageous for a variety of mechatronic systems and other fields such as, say, digital communications. An additional advantage in terms of digital signals is its flexibility. The flexibility of having my digital, let's say, zeros and ones, high and low states, is ultimately enabling this notion of software, using the software to control, say, my mechatronic system and the associated behavior. And an additional advantage of digital signals is really going to be manufacturing. If you look at systems comprised largely of analog components, resistors and capacitors, let's say, they're going to be orders of magnitude larger in terms of their packaging than the digital systems, which are really composed in terms of transistors, right? We're getting transistors down into the tens of nanometers on that type of scale. We're packing an incredible amount of hardware and capability into small, typically silicon wafers. So devices that are built upon these digital signals, such as your Arduino microcontroller or various other computer components, let's say, they're really built upon the binary signals where there's really two interpretations of these signals, of these digital signals. We could talk about a signal as being a 1, a high, a true, or an on. So this would be typically associated with, say, like a high state. We could also talk about the signal being a 0, a low, a false, or an off. So we would typically talk about that in terms of a low state. And these are what's known as digital abstractions. Now, if I were to look at this in the real world, let's go back to the system or the sensor, and let's look at just the voltage here for a second. I could define two states voltage high and voltage low, let's say, and anything above V high or anything below V low, I would associate these signals as falling into those two binary categories. Okay, so this is what you would experience with a real world system. So these binary digital signals are including ones and zeros, two different states. However, we can very easily represent more than just a 0 and a 1, right? We can combine effectively zeros and ones into larger numbers. So we can define a bit as a single 1 or a single 0. Now, if I have 8 bits, I have a sequence of 8 bits, that defines a byte. An example of a byte might be 1011 0101. And I can also define what's known as a nibble. This is a 4-bit digital word, where an example of a nibble will be a 1010, let's say. So working with binary numbers is going to require a bit of a shift in our way of thinking. We're accustomed to a base 10 number system, right? Because we're born with 10 fingers. So if we were to find the number 351, for example, in base 10, I could write that as 3 times 10 to the 2, that'll give me 300, plus 5 times 10 to the 1, that'll be 50, plus 1 times 10 to the 0, right? That'll be 1. 300 plus 50 plus 1 is 351. That's in base 10, right? Where the 10s are my base and the 3, 5, and 1 are my digits. So if I have a combination of m digits, let's say, I'll give myself in base 10 to the m possible numbers. So for example, in the case where m is equal to 3, I can write numbers from 000 all the way up to 999, right? That gives me 10 to the 3 possible numbers. Okay, that's 1,000 possible numbers I could work with in the case where m equals 3. Well, what if we only had 2 fingers? Well, I would be operating then in a base 2 system. Let's take a look at the number 6 that we associate with the more traditional base 10 system here. The 10 being the subscript indicating base 10. If I wanted to describe that now in a base 2 system, well, my bases will be 2, and my digits can only be 0 and 1. In the base 10 system, I could go 0 to 9, but in a base 2, I'm limited to 0 and 1. So 6 in a base 10 will be described as 1 times 2 squared, which is 4, plus 1 times 2 to the 1, which is 2, plus 0 times 2 to the 0, or 0. That'll give me 4 plus 2, which is 6. So I could write that out as 110 with a subscript of 2, where the subscript is implying now that I am operating in a base 2 system. So if I have m digits or bits in a base 2 system, that'll give me 2 to the m possible numbers. Let's look at the case where m equals 3. That'll give me 2 to the 3, or 8 possible numbers. So I could write these numbers from 000 all the way up to 111. In the case where m equals 8, that'll give me 2 to the 8 possible numbers, or 256 possible numbers. In the case where m equals 10, that'll give me 2 to the 10, or 1,024 possible numbers. This is what's referred to as a kilobit. So if I'm operating within multiple number or base systems here, I need a means of going between, say, as you see here, base 2 and base 10. I need a means to go back and forth between the base systems. So let's take a look at an example here. I'm going to go from base 2 to the decimal base 10 here, okay? And I have a 9-bit digital word in the base 2 system here, 1010 11111. Now, as we saw in the previous example, we can write that by adding up our bases of 2 and now multiplying by the associated digits. So let's work that out. So I have 9 bits here in terms of my digital word. So I'm going to go from 2 to the 0 all the way up to 2 to the 8. And I have the leading coefficients here, 1, 0, 1, 0, so on and so forth. So if I start writing that out, I'll have 1 times 2 to the 8, plus 0 times 2 to the 7, plus 1 times 2 to the 6. And I'll continue all the way down until I end up with 1 times 2 to the 0. So if I start adding some of these numbers up here, 1 times 2 to the 8 is 256. 2 to the 6 is 64, and if you add everything up, This will end up equaling 351 in the base 10 system. And we can also go between a decimal or base 10 system to a binary or base 2 system. So here I have number 51 in the base 10 system, and I want to convert this over to the base 2. Well, it's pretty straightforward to do following this algorithm. So let's get started. First thing I'll do, I'll take 51 and I'll divide that by 2. 51 divided by 2 will give me 25.5. So I have a remainder here. So let's go ahead and write a 1 under the base 2 column. We'll then take the whole number, 25, and divide it by 2 again. 25 divided by 2 is 12.5. Once again, I have a remainder, so I'll go ahead and write a 1 in the base 2 column. Now I'll take the 12 and divide it by 2. That'll give me 6. 6.0, I have no remainder, so I'll write a 0 in the base 2 column. Let's take the 6 divided by 2. That'll give me 3. 3.0, there's no remainder there. Go ahead and write another 0 in the base 2 column. Now I'll take the 3 divided by 2. It gives me 1.5. I have a remainder, so I'll write a 1 in the base 2 column. And lastly, I'll take the 1 divided by 2. That gives me 0.5. I have a remainder, so I'll write a 1 in the base 2 column. And I now have a whole number of 0, so there's no further division required. So the number 51 in the base 10 system can be represented in the base 2 system as 110011.